Okay, let's get this show on the road. With John in Japan and Luke, who I thought was off on a family emergency thing, but who suddenly turned up. It fell to the secretary to stand up here and introduce everybody. So good to have you along. It's a really good turn up tonight. And I'd like to welcome Dave Minchin, VK5KK, who dropped me an email about a week and a bit ago and say, we've got a deal for you. And it was too good a deal to pass up. The downside is that council decided to do some of the things that I've been angling for a while and make a start on the hall. So we've got new stairs out the back and a new door, and they've stripped the front entry. That's going to be painted next week, so you'll probably see a scaffold go up, and that'll all be painted and then retread, so replacing external lights with LEDs. So we're actually finally getting some traction on the hall, so that's good news for us. So without further ado, Dave, if you'd like to come up, you'll be the MC for tonight. And welcome.
Thank you, David.
And to our guests, Hans and Wolfgang, thanks for coming along tonight. And we'll hand it over to you and we'll sit back and listen in. I might sit right at the back away from the RF.
Okay, welcome everybody. Just a bit of background. Wolfgang and Hans have looked after us and Alan, VK3 XPD, when we've done our various expeditions to Europe, and this is, I think, the return favour. It was about a year ago, said it's time to come to Australia, and wanted to see a bit of Australia. So we're on day 5 or day 6 of the tour, which looked at various sites, done some operating. We went, the guys wanted to see the Parkes dish, because they've seen the movie, so we drove there. It's about the easiest way of getting there, and went there on the same day. All the fires are raging in New South Wales and there was dust everywhere, but that didn't stop us. We worked 122 up and down the road, just outside where you're actually allowed to operate RF. The dish was in maintenance mode, setting bird bath. There was that much wind. And we've done some work on the way back down. So it's a bit of a road trip with a little bit of operating, but certainly trying to catch up with different groups. We caught up with the Central New South Wales Club at the dish and met their members, so today is basically going through here, and good. Thank you for all turning up. Now it's fairly informal. There's no PowerPoint, so we're going to have a few demos of what we do. I think I'm first person up, and then Wolfgang will talk about his gear. Then Iain will demonstrate his software on one of the projects we're doing. So without further ado, I'll grab some props. I'll grab one of these microphones. How's that? Travelling to Europe, we found, as always, is a compromise in what you can take, and as far as equipment goes. If you want to work any decent distances, it has to be something that is portable, something you can put in your bag, and something you can change bands very quickly. So this is the system we've used for 3 years. It's a NEWRAD dish, and it's a Cassegrain dish. They're available from the US. A few years ago. The whole idea is it's a cassette transverter system. So you align on, say, 24 gigahertz, get that lined up, and then there's various other, let's have a look. One there was one here before. Where did that go? Oh, there it is up here. That's actually 76 gigs. So the whole idea is you align it on basic frequency and work your way up. If it doesn't work on 76, go back to the band below. So it's a very simple arrangement. The transverter is 2 watts on 24 gigs, 1 watt on 47, and about a quarter of a watt on 76. So all this packs up into a bag. The other bag over there is the FT817 bag. It's all up about 15 kilos. For talkback, we use 10 gigs. And this is a 4 watt 10 gig transverter with a panel antenna. Antenna is about 25 dBi. It runs 4 watts, so it's quite capable of rain scatter. It's worked about 12 countries, which sounds really fantastic. It's a bit like working VK5 from here. But it's GPS little locator on there, so that's a handy logbook when you get paper. You just take a photograph of that for each contact and save it under the call sign. So that's That's the talkback. So all that is about 15 kilos shipping. The transverters usually go with me on board as carry-on because that's the last thing you want to lose. And the joke with that is it's usually chained with a handcuff to my hands that doesn't leave my side. So that's the gear we take away, and we use this a fair bit around Australia because it works. For most distances we're working, that size dish has plenty of gain, it's quite directive. More recently, this is after Alan's article in Gibus about Cassegrains, started looking at using larger dishes. Now, Cassegrains probably, it's not a black art, it probably is a black art in the sense to get everything right, but there's a unique relationship between the feed pattern, the hyperbola, and it's not a straight hyperbola, and the dish. A lot of mucking around, but you can get there. We were doing some tests the other day with this up against my trusty, reliable 47 gig made out of fittings shepherd's crook. Got it to the point where there's less than dB difference between the two. Now the whole idea of this is exactly the same. Now I usually don't use this on 24 gigs, but it's the same cassette arrangement, longer feed. So once you line it up 47, you can put 76 in. And one thing we found with the Cassegrain, it's always handy to have a little bit of play to adjust the focal length. Everything's good in theory, but generally it's a few millimetres backwards and forwards so you can give it a bit of a peak. The Cassegrain is not made of metal. It's been 3D printed and just covered with foil. And that's fine for a Cassegrain. You can get the shape right, you can experiment. The hyperbola actually has three. To describe how the hyperbola must work, a horn feed, as you'd all know, isn't a linear feed. It has a taper. So the Cassegrain has a bias such that power from the centre is actually spread out. And if you think about it in theory, your first reflection you actually want to miss the Cassegrain. So the three factors, two relate together, one relates to the actual taper. Once you get that right, you can get a fairly good feed pattern. The easiest way to check this is to get the sun and just run water over it. It reflects really well, and just get a bit of paper on the end of a stick, and you'll soon see. If you've got a nice dot, you know it's working okay. So it works 24, 47 and 76. 76, probably 140 Ks or something like that. 47 we've gone further with. So that was the development from that one there. So that's the equipment we use on 24, 47 and 76. Now I'm going to hand over to Wolfgang. Wolfgang's now going to discuss his 122 system.
Thank you. My call sign is Oscar Echo 4 Whiskey Ocean Golf, and I'm glad to be here together with Hans to visit also faces we know from Friedrichshafen when we met together in Lake Constance, or what we call the Bodensee, in the edge between Germany, Austria and Switzerland, which is a big ham fair. You probably know about that. And since a couple of years we have done a lot of expedition around this lake, taking all the big hills and the big mountains. And this gentleman brought over a lot of equipment, of course. So, and we thought it's just time to do it in the reverse way. So we come over to Australia. First of all, it's our first time. So we appreciate to be here in this very, very nice country. And we brought over 122 gigahertz equipment, also for do some testing, and then we are aware that here are running 122 gigahertz projects, which have been found as very interesting for us as well in Europe and somewhere else, of course. And there are two projects, and Iain and David will talk about this one later on. And we will see which one is will bring us a lot of, let's say, features for the future. What I have here is a simple what we call the bar mixer design. It consists basically of passive elements on the RF side. It's just diodes. They are doing the LNA, and the same diode is doing the transmit mixer, for example. You can imagine this is not very sensitive system. On the receiver noise figure, we are around 30 dB. If we are 27, we are quite happy. On the output power, we are in the range of minus 6 dBm or 250 microwatts. The only way to do better is to provide on the transmit side a TX only element, which consists only of a tripler. So in this way, we could achieve 1 milliwatt output. Fortunately, the antenna can do a lot of things for us. Precise antennas give you quite a lot of gain. Like the simple one, we took only the 20 centimeter dishes with us because of the luggage and all the weight. Normally we are using 40 centimeter dishes, and in the meantime we went up to 1.2 meter dishes, especially using not the prime dishes anymore, but we are using offset dishes. So, of course, as far you go up with the antenna gain, your beamwidth gets smaller and smaller, and there's it's a real challenge to find your partner on the other end. We solved that in that way that we built antenna systems that we can feed up with 3 centimeter, 24 gig, 47, 76, etc., etc. And we start, for example, if we do a test or a DX or whatsoever, like contest, we start with the lower frequency. It's very easy to catch up with the partner station and adjust the alignment roughly, go to 24, do a better alignment, change to 47, make it more accurate, going up to 76, and so on. But the antenna will always stay in place, so we don't have to change the triputs or something else, and we will have a correct aligned antenna to the partner station, and then you can use it also on 122 gigahertz. Even on this frequency, your beam width is around 1 degree. This one here is the old concept, as I said before, a bar mixer concept. We have an RF head here, which is holding the diode. The diode is sitting over a waveguide opening, and the waveguide opening goes into the feed and into the antenna. The power comes from a 40 gigahertz amplifier, which is overdriven, so he produces around 100 milliwatt LO power, which is the incident power into the diode. The diode by itself must mix TX 2 meter or 40 or 70 centimeters, including the LO, and also must do the tripling. So you can imagine that the efficiency is quite low, and that's the reason why we have only 6 dBm single sideband output, if we are lucky. And everything is made in the correct order, of course. The 40 gigahertz will be phased from a DRO. This is sitting here underneath. The DRO is referenced around 100 megahertz, and the 100 megahertz approximately are referenced again a 10 megahertz reference or even a GPS. So we achieve at least a very good frequency accuracy, and this is not a problem anymore, because in the old days when we started with this 10 years ago, then we had plus 60 degrees, plus 60 degrees centigrade, sorry, OCXOs, and you never know where your final frequency was. So there was two things to do. One side we have to find the frequency, the right frequency to find our partner, and on the other hand it was also critical to find the right direction. In the meantime, the frequency problem is fixed, no problem at all. So this works quite well, and we brought this over knowing that you are working on much better, or let's say future approaches for 122 gigahertz. Here, this one here, I started exactly 10 years ago with 122 gigahertz, just running 1 kilometer. In the meantime, we have improved these things, and we think that we are on the limit. So our best record we achieved was 132 kilometers on 122. But I have to say this is also weather dependent. That the biggest point, or let's say our biggest problem, let's say in this way, is the atmospheric losses which we have in addition to the path loss. And so you can imagine on additional atmospheric loss of 0.5 dB per kilometer, it will eat you up very quickly, your margin on this connection, on this path. But this is also, I think, very well known because these are physics. So I don't have to go deeper on these details. Let's say it in this way, this approach here as well, this one here, the TX transmitter, is basically the end of that technology, let's say it in this way. You can't go better than this one. And that's our experiences. But yeah, up to now it makes fun to find out the different conditions occurring on this band. And today, or this week, we have used this equipment also to go in touch with these two gentlemen to make some bench tests and share experiences as well. The good thing is we found out that makes us very happy, as we are running 122.250 straight away. That's the, let's say, normal European frequency band, or the frequency allocation we have. We can easily match up with the VK5 project in terms of the same frequency. So we can mix the old, so-called old technology with the new one, which is quite an improvement also. It's, we are happy to have that because we have done the same people which can do, can share QSOs and make QSOs. I think that's a very important fact that we stay on the same frequency concept. Yeah, that's basically all what I can say about that. And would leave the microphone to the new technology. Thank you very much.
Thank you, Wolfgang. It's some technical details on this. I think it's 10 micrometer accuracy or something like that, around that region. We were doing some tests the other day and testing the alignment, and a dish that size on 122 is still razor sharp. It's point whatever degree. It's amazing. It works exceptionally well. So it's, and I've actually seen the 1.2 metre dish that Wolfgang referred to. It belongs to Rudy OE5 BRL, who's best described as the master machinist. It was an old cast dish that he resurfaced. Now have a think about that, 1.2 metres. I think the lathe had a 4 metre diameter bed or something like that, used for making gas turbine parts. So And I saw the drawings, and it was every measurement was plus or minus 0. So, but beautiful technology. We can only try and get somewhere near it. There's certainly a lot of, no matter what the technology is, that the antenna is the bit that's really going to make the difference. Wolfgang mentioned about atmospheric losses, and this is something Iain has for nearly 10 years. Is it 10 years? Has hosted a website for the South Australian Country Fire Service that gives a rating on fire danger, and it basically takes live data from the bomb site. And I'll hand over to Iain. It's some of you may be aware that Iain's created a website. Initially it was for SA, but now you can dial in your local weather station and it will give you a prediction on the path loss on 24 up to 241 gigs, I think it is. So based on IEEE calculations, here we go. I'll hand over to Iain. Here we go.
Okay. Doesn't matter which microphone I use, does it? Let me just get this thing to the top of the page. There we go. So we're on Victoria at the moment. So the Bureau of Meteorology has a whole lot of automated weather stations scattered around the country. And you can, on their website, they have a page where you can go and look at the current observations from every weather station. And they're updated roughly every 10 minutes. So what I've done is I've written a little piece of software that goes and grabs the observations page for each state in the country and strips out all the HTML and basically extracts the relevant data from that, which I upload into a SQL database. So I've actually got, not the whole country, but for South Australia at least, I've got reading every single weather station reading going back 7 or 8 years now, if I ever want to look at anything historically. But when we started doing this, and we realised that, you know, atmospheric absorption plays a big part in particularly 76 and 122 gigs, I went and started looking at the maths involved in working out the absorption losses. And for some reason, we're up to like version 9, I think, now of the maths, and I'm thinking, you know, does the atmosphere actually change? You know, I would have thought physics would be fairly constant, but anyway, they keep amending the calculation for whatever reason. But essentially, there is a whole lot of absorption spikes at various frequencies. And the maths involves basically for each spike working out what effect that spike's going to have on the frequency you're interested in, and then summing the results of all of those together to get a final absorption figure. And what I've done is that this is the website I've got up. You can click on one of the buttons at the top to get what state you want to look at. And the interesting numbers are this one here, which is the absolute humidity, moisture in the air in grams per cubic metre. And that's calculated from the relative humidity, the temperature, and the barometric pressure. The barometric pressure doesn't have much effect, small effect. This number here is what determines the losses you're going to get at the various frequencies. And that's what I've calculated and displayed on the end here. So I show numbers for 24, 47, 76, 122, 134 and 241 gigahertz in dB per 100 kilometres. These numbers have to be added to the normal free space path loss calculation. So that's in addition to whatever the loss is, just because you're 50 k's apart or whatever. So, you know, as you can see, if you want to play on 241 gigs, you do not want a humid day. You know, Ararat, 92% humidity, 443 dB per 100 k's. Your signal is going to go jump like that very, very quick. Ideally, I mean, you look at 122 gigs there, even with, you know, dew point's the easiest thing to look at. You can get little handheld meters that will show you the dew point. That's a good indicator. It's not quite linear with dew point, but close enough. But, you know, even here, where it's moderately, you know, average, I guess, 6.5. When we were playing the other day, we were attempting a 76 gig record and it failed dismally because this was just too high. It was around 7.2 dew point, which as you can see equates with 37 dB per 100 Ks in addition, and we were 180 odd Ks apart, and it was just way too much. I think it was a bit higher at the other end, so I've actually arranged this thing so that if you do have a low, see if there is a low one, where's it going to be dry? Northern Territory is normally dry. Yeah, let's try NT and see what comes. Oh, there we go. Alice Springs Airport, dew point minus 10.7, right? So now the losses on 122 gigs are down to 34 dB per 100K, which is way lower than this one here, where you've got a 23 degree dew point and the losses are 221 dB per 100K. So, you know, as Wolfgang said, weather, the amount of moisture in the air plays a huge part in exactly how 122 gigs is going to behave, and 76. I mean, it's as you go lower in frequency, the effect is less, or the absorption is less, but given the number of 122 gig boards and things that have been ordered from, I can't remember the chap's name, Tim somebody, to XAX as the project. You're definitely going to need to be looking for the days with very low humidity if you want to get any sort of distance out of the things. So this website's there, weather.vk5microwave.net if you want to go and have a look at it. And the info button on the end gives you some relative guff about how it all works. And if you want to go and look at the maths involved in calculating, you go and click on that link down there and you'll get this PDF file from, I can't remember where it came from now, but yeah, it's ITU something or another, document number, big fancy number. That's it there, there we go. Recommendation ITU-RP676-11 of 09-2016. It's version 11. That's what I said. I don't know why physics keeps altering, but there you go. Okay, I think that's about covered that. If you would take the mic back.
Thank you, Ian. Excuse my throat. Okay. So that's we've probably for a few years been calculating this and carrying around little meters and working directly at dew point. But when you actually visualise what's happening, it's an amazing tool. You can. We're starting now to work backwards on what we're actually seeing in the field, working back on calculations and getting pretty close, but there's always variable bits in there. And what we're looking probably at next is, and this is getting to the stage we need to do some actual research with, say, beacons over short distance and just see. It's probably why there's 11 versions, because you can actually see a change in the data as they've gone through over the years, as there's been more research done on 94 gigs and things like that. But and oxygen. It doesn't vary much. It's certainly better at higher altitude, because, especially for 122, because oxygen is a significant factor. So if you're 3,000 or 4,000 metres up, it will be better than when you're at sea level. But water vapour is best. You know, weather is everything, I think, is the catchphrase Iain coined a few months ago. Okay, next bit. Now, Wolfgang referred to technology, and there's a bit of a story behind this. And probably the first time I knew about the new chip, the chip that Andrew's used and we've used as well, was in 2017. And Henning, DF9IC, when Silicon Radar were first marketing these chips, and marketing is probably the best word, because it's not venture funded, but they're associated with the Frankfurt University. There's a number of different companies involved there. And they've created an amazing 60 gig push VCO. When I say amazing, it's the actual way the oscillator works and the results you get are quite good. You know, generally on-chip phase lock loops will always be lesser quality as far as phase noise, as far as jitter and all those factors, versus something which has got a high IQ resonator. But for something which is essentially on chip, it's an amazing chip. So Henning did some work with that. He I think professionally did 25 samples, and his first report was lots of phase noise. And I think we've all been with that, same thing. And that's probably various different factors in that. Zooming forward to it was K6ML, Mike Lavelle. He published last year's and this year's microwave update, his version, which was based pretty well on the development kit that Silicon Radar had out. You can buy a Silicon Radar development kit if you want to play around with radar, but it's relatively expensive, and for what we do, nigh on useless, because it is actually a radar unit. Andrew, VK3TV, started playing around, probably it was last year, I believe, started. So it's been going for nearly a year now. And that now is basically available on a GoFundMe type project. Over 300, I believe. Yeah, it's amazing. It's a great project. Hats off to Andrew, because it's probably the thing we've needed for a long time to kick activity on microwave. Be a lot of learning with people. It's one of those things that the design will be solid. It'll be the mechanical bits, antennas and things like that. But there's a complete file. Around May, we got news from Kuhn Electronics that their printed circuit boards that are used in these types of multipliers and transverters are finished. So that kicked a couple of people into gear to say, okay, where are we going to go? There's certainly the alternative is there to create another printed circuit board, but the known factors, some of you may remember I ran equipment suppliers committees for many years, and we did microwave kits up to 24 gigs and etched 580 Duroid and everything else, and all the challenges of getting a board done, it is very difficult to get something. The boards that Kuhn marked, it was actually Michael Kuhn's wife, Jutta, I think, used to do the boards. And the boards have certainly become unavailable because the material, the 10mm PCB is still available, but the company that coated it with photoresist has closed, and they actually haven't made boards for quite some time. So there's no more boards available for 122 or 241. The artwork's there, but that was probably the final straw. I started looking at, I was at Friedrichshafen and started talking to different people, and okay, which way do we go? So that's created a different approach to Andrews. We're looking at the receive side of things, because we can develop power. You know, if those that already have 122 probably have the ability to create quite a bit of power, so certainly a tripler is the best way to go. And so we're looking at something which is a better receiver. Now the chip is an amazing chip. It has a quadrature mixer, so you've got both I and Q outputs. It enables you to create an image reject receiver. It can be tuned across a whole range of frequencies, but certainly the switching is like microseconds between frequencies. So what we set about was to do something which was image reject, and also something which we could use for direct digital modulation. The phase lock loop we're using is ADF 4159. That has an FSK input, but what we've found through testing is that you can switch the frequency very, very quickly. It's 1 or 2 registers can be loaded, and it's quite possible to modulate tones. I think we can get 38 hertz separation or something like that, so you can do JT4F pretty close, or JT4G. So that was the motivation on that. It's still a work in progress. Certainly specs, we're quite happy. Probably hardware we've got settled. Ian has developed the software. My basic software was just that, basic. He did the sort of RX and TX. So Ian, do you want to plug in? I'll do a bit of a demo on the software.
Yes, there we go. David designed the board with a Arduino Pro Mini as the device to control everything with. So that's on a little separate board that plugs under the top of. Well, here's his board, and you can see the Arduino board sat on top up there. Yeah, pass that around. So I've dusted off my C programming skills, which are virtually non-existent. I think this is the biggest project I've ever done involving C. So it's been a bit of a learning curve, but we're getting there. Anyway, let me just scroll up a bit. That's the help file. You just enter a question. This is controlled just through a terminal program on the laptop. So it's just chatting with this via a serial terminal. I've added a type of question mark, and you'll get this list. What I decided to do initially was set it up so you could control every single parameter in the PLL just by changing it from the keyboard, as well as a few other bits and pieces that are involved with this. But for example, I mean, there's the ability to load and save these parameters into the EEPROM in the chip. There are 10 preset frequencies in here. One's your transmit frequency, one's the receive frequency, and by that I mean the LO that mixes with your IF. So it would be 144 megs away from the transmit frequency normally. There is a frequency, because this thing will generate CW. There's 6 preset messages in there, which is pretty much it, same as like the JT messages. Everything you'd need to complete a QSO. Sending and receiving, call signs, grid square, signal report, with the option for extra numbers if you're contesting and things like that. So when we transmit CW, it's done by frequency shift keying, and you can set one of the frequencies is the key up frequency, if you like, which is, by default, I shift 100 kilohertz away from the transmit frequency. That seems to be far enough that you don't notice anything, but you can enter anything you like. And the other frequencies at the moment don't do anything, but they're there for when I finally work out how to generate JT4 messages. There is a Arduino library for JT4, but it only generates plain text messages, so you're limited to 13 characters. The type 1 messages, I'm head down in Joe Taylor's code at the moment for JT65 and all the other bits and pieces, and it's all written in Fortran, which I've never seen before in my life, so I'm trying to change Fortran, which I know nothing about, into C, which I know just a little bit about. So it might be a bit of an involved process, but hopefully I'll get there in the end. So the other frequencies are the frequencies necessary for JT4 modes F and G. I can also change all the charge pump settings, and you get some interesting effects change in that, which I'll tell you in a minute, but I can't explain it. There's a bunch of parameters here where I can set up Morse code stuff, so MC equals whatever your call sign is, MO equals whatever the other call sign is, MR is your signal report you want to send, MS you can set the speed from 5 to 30 words a minute, or you can just press M in a question, it will show you what all the settings are. There's a function in the PLL called negative bleed, which slightly cleans up the signal, or slightly reduces the noise, I should say, the phase noise. There's the reference parameters, so there's a doubler, divider, and the reference counter. You can set all them to whatever I want. And if I go and change the reference, the reference counter at the moment is set to divide by 1. The reference frequency is 20 megs. But if I go and change it to, say, divide by 5, so the reference becomes 4 megs, it'll automatically recalculate the other bits so the frequency doesn't alter. That's all done in the code in here. So I can experiment with different phase detector frequencies and just change those numbers and instantly see on the spectrum analyzer exactly what effect it's having on the signal coming out. What else have I got? Further down the list, there's a ton of things you can set in this PLL's registers. An awful lot of it to do with its life as a radar chip. It'll do ramp the output signal with a sawtooth up and down in frequency and things like that. And there's all these different settings that you can put into the PLL chip. I've made them all configurable, but I've never had to play with any of these things. They'll all be just fixed in the code. And once I've taken all that out, there should be enough room for the JT4 stuff because I've run out of memory at the moment. This chip's got a pin that's supposed to control the TX output power by 6 dB according to the data sheet. Measurements indicate it drops at about 1 dB. You know, it's hardly worth worrying about. Now the other thing we've noticed with the charge pump is changing the charge pump current alters the amount of power that comes out of the chip, and I cannot for the life of me work out why that would be so, because the silicon radar chip, it's just got the VCO in it. All you're giving it is a control voltage for the VCO, nothing else. And when you change the charge pump current, it doesn't go out of lock, that voltage stays the same. But you look at the output spike on the spec end and it would creep down like that as you wind the charge pump current up. And I've got absolutely no idea why that would be so. Maybe someone here can brainstorm that one.
Changing the phase noise characteristics of the whole loop. You change the current, and so you're putting more power into the noise.
Yeah.
And it's almost indiscernible with the carrier.
I was going to say, you don't see the noise level change at all.
Yeah,
it's just
because it's
all spread
everywhere.
out. Yeah.
It's like so far spread out from where the carrier is, you don't even
I knew there would have to be a reason, but just looking at it, I'm thinking, why the hell is this?
I've chased exactly the same thing.
Yeah.
I've chased it down, and that's all I could put it down to.
The chart where the filter's been designed,
Yeah.
that's where it's spot on.
Yeah.
And then as you go higher, it drops.
Yeah.
Yeah, that makes sense, yeah.
I'll just reset this thing by turning the power on and off. Now when I start it up, it comes up, so it started here. It's telling me that the phase detector is currently at 20 million hertz. Everything's in hertz, by the way. And the resolution there is 38 hertz, so I can change the frequency in 38 hertz steps. If I change the phase detector to run at 10 megs, then that will become 19 hertz steps. And I'm thinking 19 is probably quite adequate for the JT4 F and G modes. You know, that's accurate enough. These are the 10 frequencies programmed in at the moment. So we've got the top one's the transmit frequency, 122.250.24. And for receiving, 122.104, which is 144 megs away from that one. These ones here, numbers 3, 4, 5, 6, and 7 are the JT4 tones for modes F and G. Some of them are common. Number 8's not doing anything at the moment, and number 9 is the key up frequency. And this is what's actually been written to each of the registers in the PLL chip as a binary and a hex number, which I thought might be useful to see what was going on, but in the end it doesn't matter. So I mean, I can turn the transmitter on and off. I've got a switch on here. It's been received on that one over there. Or I can just type TX on here and that'll turn the transmitter on. RX turns it off. I'll go and look at my Morse code settings. So I've got my call sign, my grid, not that it's correct grid here, that's my home grid. Dave's call sign, a report, a speed, a tone. The tone, there's actually a little audio sander inside this thing here, and it generates, so you can hear what you're sending. Data repeat, sets whether or not I want to send the call sign, the report, the grid twice or not, or just once. And the key up frequency is frequency number 9. So I mean, if I wanted to send a CQ, that's message number 1. So I just type M1. I've got the repeat on, so it's doing call sign twice and grid square twice. Meant to turn that off. I've got a noise reducing speaker on the receive end just to cut out all the hash that's there when the key's up. But given that it's a VCO running at 60 gigs being doubled to 122, it's a fairly clean sounding tone. It's quite a remarkable chip, this thing. I think that's about it in terms of what we've done here, software-wise. The next version will hopefully have the JT4 option in it. I'm looking at 2 ways of doing that. One is write all the code to do the JT4 in here, or the second option is to measure the frequencies coming out of the laptop on transmit and turn them back into numbers that change the frequency. So I'll just use the standard WSJT program in the laptop, have something that will physically measure the tone frequencies as they come out, and use that to decide what I'm going to transmit out of here. So I'm a bit of mixed minds which way to do it. Working out the tone frequencies is probably the better option because it lets you use any of the modes in there, provided the steps, you can change the frequency by a small enough. I mean, you couldn't do JT65 because that only moves a few hertz, doesn't it, between the tones. So we can't, with a resolution of maybe 19 hertz. If we make the phase detector frequency lower, the noise comes up. It just gets worse. So I want to keep that as high as possible. So it's a bit of a compromise between highest possible phase detector frequency versus the error in the tones being generated. So I think probably 10 megs would be the go for that. But once JT4 modes is in there, that will automatically do that. So when you say I want to send something in JT4, I'm going to have it just change the phase detector to 10 megs, send the stuff out, then flip it back to 20 again when it goes to receive. And on the receive side, it will just be the normal Joe Taylor software. I'm not trying to work the receive half of it out. It's too complicated. Okay.
Thank you, Ian. Okay, actually, a good point there, Andrew. That was something discovered very early. I actually used an active VCO filter. The filter is set at 100 kilohertz, and I think charge pump 1.2, because normally when you double it, you max 2.5. And I think that's exactly where it peaks. It's somewhere from there, or about 0.94. So that makes good sense, because the amount of noise, it is certainly, you only need a few dB out here and the power drops into it. So it's one of those interesting projects that actually worked pretty well straight away, which is always a worry. And then we sort of chase down little things like this. But phase noise, to put it in perspective, my phone, watch going flat. The nearby is probably about minus 35, minus 36. Put that in perspective, that's actually better performance than we get with our current transverters when we're using different oscillators. We did a bit of a comparison the other day between a range of different transverters, one using an LCOM, one using a Kuhn oscillator. Previously I've compared with the ZL2 BKC 13 gigahertz PLL. And to be honest, the silicon radar is pretty well up there at the top. No one here from Kuhn. The Kuhn wasn't actually the best oscillator. There's quite a bit of jitter. Wolfgang has a CTI Dro. That is quite good. That's certainly a different, rare beast you find on eBay these days. On 122, we're happy to see something that's mind us, we're not trying to chase something which is commercial spec on a lower frequency. And if anything, it's the signal purity, lack of jitter, very important for digital work. So that's the project as it stands at the moment. We're just moving along with probably a few other enhancements. FM, if anyone wants it, basically moving the reference on the VCO filters, it can get enough to move the oscillator. Ian's project looking at recovering the JT tones. That's possibly the way we'll go, but it requires a higher power Arduino. So we'll certainly look at that. There is a lot of interest in running digital on these devices, and it's something digital at 122 has been limited by the purity of the oscillator previous to now. And Ian and I have done quite a bit of experimenting one day, just trying to get that to work over a short distance, and then it was all about the oscillator. It's not about anything else. We might wrap that up. What do you reckon? Okay, feel free to come up, ask questions. Anything you like, that's fine. Happy to answer them. Thank you.
Thanks, David. And what a great presentation. Thanks to everybody for coming along and enjoying this.